Hey everybody, Lars here. I'm glad to be back. It's been a while since I did one of these videos, and it's been a while since I've been normal. As you guys know, I've been going through a lot of garbage with my leg situation. My second surgery for my Achilles tendon, as most of you know, ended up being infected. So they had to go in and clean it out, and when they cleaned it out, there wasn't a lot left to close the leg back up with, so they had to leave it an open wound for a week, and then they went and they did plastic surgery and they closed it back up, and now it's been a week since that surgery, and now that's healing up, but it's feeling kind of crummy tonight. So it's definitely been a weird journey, but I've done my best to keep up with the Python class, to keep things going, to keep you guys going, and to make sure you get all the resources you need to make sure you do all of that stuff. So Unit 4 is underway now, so I figured I'd get you that first video, which is just an overview of different CS topics. And whenever I do this video, I always start by saying, back in the day when you went to university for a computer science degree, you took your first class and it was called Introduction to Computer Science. It wasn't called Intro to Programming. It was called Introduction to Computer Science. And what would happen is you do a lot of the things that we've been doing. You learn about simple data types. You would learn about sequences. You'd learn about lists. Only back in the day we called them arrays. And you would learn about a bunch of other things. But all of a sudden, about maybe a month into the course, universities would start sneaking in computer science concepts. And I always thought, as far as just learning how to program, that sometimes they got in the way. If the purpose is to become a computer scientist and learn about computer science, well, then it's the proper way to do it. But if you just want to learn how to program, sometimes these things can get in the way and make things confusing. So when I developed this course, I purposefully extracted a lot of the computer science content, and I said, let's learn how to program first. So you spend the first 3 units of this particular course learning how to program. You get data, you get arithmetic, you get booleans, you get sequences, you get strings, you get lists, you get loops, you get functions, you get modularity, you get file I/O. You get all of those basics that let you become an imperative Python programmer. And then afterwards, this is the unit where I throw all the computer science back at you. So in Unit 4, you're going to see a little bit about sorting, some stuff about searching, some ideas when it comes to something called Big O, algorithm analysis, and at the end of the day, and this is for another video, not even this video, but we're also going to look at recursion. So, but today, we're going to look at the first half of the Unit 4 slides. Unit 4 is a regular 2-week unit, get you back into, a little bit of normalcy after the long, arduous craziness of Unit 3. And I get it, I know. I'm going to shoot, because of my leg and because I can't get around, I had to miss the in-person class for Class 3, but when I do the video for it, hopefully this weekend, I'm going to go over the homework assignment for Unit 3. So you'll see what I do with Harshed and Siete and cleaning up the data file and going through all that stuff. But let's worry about the first half of Unit 4. And let me go here, and we will begin by looking at the slides. There we go. Let me do this. So let's start with sorting. Again, I go back and I always tell the story. About 1 month into your class, when you start going to school to become a computer scientist, you're taking that class called Intro to Computer Science. And about a month in, you are introduced to sorting. And for the next couple of weeks, sorting becomes the bane of your existence. You learn about the bubble sort, the quick sort, the J sort, the this sort, the merge sort, the that. And when you are 19, 20 years old, like I was, and you start getting all these sorts thrown at you, you're like, oh my God, this is so tedious. This is so crazy. Why are we doing this? 30 years down the road, when you become an old fuddy-duddy like me, you realize why we were doing it. And the reason we were doing it is because by examining sorting algorithms, you can begin to look at the analysis of algorithms and learn that some algorithms are more efficient than other kinds of algorithms. Immediately, one of the first things you'll do is you'll learn how to do a thing called a bubble sort, which is basically two things. You compare two things. Really, is one greater than the other? Then switch it. Is it not? Then don't. Then go to the next one. Go to the next one. Go to the next one. And at the end of the day, I mean, that's all sorting is at the end of the day. Should something be switched to put it in order? Then switch it. Boom. So, but believe me, there's a lot of different sorting algorithms, a lot, and some many more times efficient than others. And you'll see as we go through this. So there's some method to the madness when you start getting sorts at a young age. Professors will, show you the different sorting algorithms, show you how to work, and say, is this more efficient than this? Is this better than this? There's lots of ways to sort things. There's lots of different orderable lists. You can do alphanumeric. You can, do numeric by number. There's not just a list of things to sort. There's always a sortable order. There's always a way to sort things as well. There are many, many different sorting algorithms out there. And what usually happens is at the college level, when you hit that first month, you will start coding up sorts and coding up sorts and coding up sorts. But again, and when I get to this point of the video, I always say this, I got to make decisions here because I've only got 15 weeks in a regular semester to teach you guys Python and then have you use it a little, learn some computer science, learn some object orientation, learn a little bit about data structures, and get it all in a data science-y way, looking towards, using Python in a data science way. So it's a lot of stuff to cover. So I don't make you code up a sort. If you're dying to code up a sort, there's a merge sort in Zell. There's bubble sorts. The world is lousy with bubble sorts all over the place. But I do want you to go to this particular website here, sortingalgorithms.com, and look at all the different sorts and how they're run and what they do and how they do it. And it's pretty neat. You can see how the different sorts run and what it takes to basically get all these different lineups and data sets in order, depending on what the algorithm is to put them in order. So that's always pretty neat. If you've ever taken a stats class, be it confidence intervals or hypothesis testing or whatever, you always go through once and do it by hand. And then after you've gone through and done it by hand, the professor will, without a doubt, say, okay, you know what? Now you'll never have to do that again. Now you can use SPSS. Now you can use R. Now you can go ahead and do what you want. Well, it's the same thing with lists and sorting. Once we make you do a couple of different sorts, we tell you, oh, by the way, you'll never have to do it again because there's always a sort procedure to use. In Python, look on the screen. We have a sort method that runs on every single list. You can sort any list that you have. If you're interested, Python implements something called the TIM sort. It's actually relatively recent. It was developed just for Python, so that's an interesting story. If you go to Wikipedia, you can read about TIM sort and look into some of that stuff and see what that's all about. Okay, so you can sort things. As you can see, there's just a regular list, and then you can sort it and print it, and you'll get the numbers all sorted out, as you can see right there in that one. Okay, now you can also have a list of alphanumerics or strings, and you can sort that list, and as you can see on the screen, that also gets sorted. So you're in pretty good shape. If you have a list of names, you can sort it. If you have a list of numbers, you can sort it. Then you run into something different. What if you have a list, and this is what's great about lists, is that you can have mixed data types. But what if you have a list of mixed data types, and then you sort it? What would happen if you ran that particular code? Well, then you would get an error. And the reason you'd get an error is because of the old phrase, you can't compare apples and oranges. Well, it's true. Okay? Apples, strings, oranges, integers, how do you sort them? You could teach the language how to do it, and if you move forward and take, a Java class or something like that, you'll learn about something called sortable or comparable, and you'll learn that you could teach languages what sorting orders are, but for just this simple case right out of the box to sort something, you really can't sort mixed data types. So whenever you want to sort a list, you're going to want to make sure that list is comprised of only things of the same data type. And then when you do a sort, you're really not going to have any problems with it. All right, that's cool. So it also begs the next question. Why do we care so much about sorting? And we care a lot about sorting because when it comes to data analysis, and this ties into big data a little bit, the more we know about our data, the more informed we can be about examining it, and the more clever we can be about coming to different kinds of conclusions. So if we can sort our data, if we know it's been sorted and can detect it is sorted, or we can sort it ourselves, then we really know something about our data that can help us as far as searching through that data and looking through that data. So sorting is important. We teach people how to sort, and we do it with an emphasis for algorithmic efficiency and things along those lines. But it's also very important to have sorted data. And the reason is, at first, is because of searching, the second topic that we're really going to look at. When we search through data, let's say I have a list of 1 million items. How many times do I have to look through that list to find something that might be in that list? Okay. Worst case scenario, if that item is in the very last spot in the list, well, then how many times do I have to look at items? Okay. If I've got 1 million items, I have to look at the first one. Then I have to look at the second one. Then I have to look at the third one. Then I have to look at the fourth one. Each time I do that in computer science, it's called a lookup. Okay. Or a look to see what things are. Well, if I've got a data item in the very last spot in that list, then I had to do 1 million lookups for a list of 1 million things, okay, before I could definitively say either that item's not in the list or that item is in this particular spot, okay? That's your worst case scenario, and we always deal with worst case scenarios because we don't want to get bit in the rear end when we analyze processes and determine how long things are going to take. So at the end of the day, with something called a linear search, we want to make sure that we have the worst case scenario, and if I've got 1 million items, I'm probably going to have to look at 1 million different things to absolutely make sure, okay? But this is where sorting comes into play. Now, well, two things. One, if I look at something and I have to look at every single item, okay, that's called a linear search because you're kind of going down the line. It's like a serial search. Boom, 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 boom. So we call that linear searching, okay? There's a second kind of search called a binary search. And it's called binary because you make a choice, one or the other. And in order to do a binary search, you need an ordered list. Because what you're going to do with the binary search is you're going to go to the middle of the list. And you're going to say, hey, I'm looking for this item. Is the item I'm looking at in the middle of the list higher or lower? And the algorithm will come back and tell you. It says, oh, you're looking for this list, but what I'm showing you is a lot higher. So all of a sudden, because you know you have an ordered list, you'll know that the top half of the list, you can throw it all away. Because if everything there is higher, then I know it's not what I'm looking for. So go ahead and get rid of it. Instantly, you've cut your list in half. So if you had a list of 1 million things, boom, you just took 500,000 of them and threw them away. You don't need them. Then you do it again. You go to the middle of that list, higher or lower. Well, this time it's lower. Oh, okay, then I could throw the lower half out. Okay, now I've thrown out another 250,000. Now I only have 250,000 left. With only 2 lookups, I've thrown away 3/4 of the list. I don't need it. I don't have to look there because I knew my data was sorted and I know where these different things are. Okay, so the power of sorting gives us efficient ways to begin to search through data sets to look for things. Okay, so that's called a binary search. Here's a real easy drawing or example of it. Let's say, what is it, 16 items? I got 16 items. I keep splitting things in half until I find what I want. Here in 5 lookups, we can zero in on exactly where something is in a 16-item list. Okay? So, I mean, it's super efficient, especially, I mean, if we just go with 1 million, I think that's what I do with the code. But as you can see, I have a function here called binary search, and it implements what we were just talking about. Now, I know when you first see it, it looks crazy and it looks complicated. Trust me, it's not. Slowly, surely, take this code, run through it, and trace through it and understand what it's doing. Because this is basically the code for a binary search. All right? Actually, you know what? Might as well let the cat out of the bag. I have it coded up right here. And I'm going to take this code and I'm going to put it on Sakai for you guys. So you're going to see in your second homework assignment, this unit, things are kind of backwards. The second half of the slides are about recursion, but that's your first assignment for homework. And then the first half of your slides are about sorting and searching, and that'll be your second homework assignment. Because it's a little bit bigger. Because I'm going to give you numbers, and you're going to do a little file I/O, and then you're going to, do some sorting and searching on it. I'm going to give you this code. Okay, I'll put it on Sakai for you. If when you do the homework, you want to use my code that I'm giving you for your binary search, I have a B search. And down here, you'll see I've even coded up a little linear search. then go ahead. That's fine with me. That's completely up to you. You go ahead and do that. That's fine. I'm giving you the code. I want you to read it. I want you to understand it. When you see the context of the homework you get, I'm going to know that you understand what's going on if you put these in a library and use them for yourselves. So what I do down here is I basically compare a linear search to a binary search. So here you have the code for the binary search. And basically all it does is it takes a number that you're looking for and a list, and it comes down here and it says, well, there's a low and a high, which means you're not at 0. So there's an interval to look at. Take the middle number, okay, and look at the middle number. Is it what I want? If it is, then return it, but usually it's not. So then what I do, I'll see if X is greater than the item. If it is, I make the high point mid -1, but if it's not, I make the low point mid -1. And what does that do? It throws out half the list. You'll see what you'll see what it does if you trace through it. You'll see how it just takes the index and whoop, it moves it up half the list. So if you've got 1,000,000, then that becomes 500,000. Then that's 250. Then that's 125, and on down the line. And you'll see when we run the code. Linear search, it's real simple. Run through a list until I find something. It's called going to war. That's all you're basically doing is you're hopping in a list until you find something, or you get to the end of the list and you say, you know what, I didn't find it. That's really all a linear search is just run through everything and look. Okay? So what I do down here is I create a list called mynums that has 1,000,000 numbers in it from 1 to 1,000,000. And then I do a binary search looking for the worst case scenario, 999, 999. Okay? So when I run the code, and you'll see this is pretty neat. Did I want to do that? No, I want to do that. I want to do that. There we go. Starts right here, and I'm looking for the worst case scenario. So in a binary search, what do I look for first? 500,000. Then I say, what am I looking for? Is it higher or lower? It says it's higher, and I go, okay, then I can throw out the bottom of the list because I know it's not in the bottom of the list. So what's the middle of what's left? 7,500 or 750,000. Okay, so that's the middle. Is what I'm looking for higher or lower? It's higher. It's always going to be higher. It's 999, 999. Okay, so then I split it in half, split it in half, split it in half, split it in half. Worst case scenario, searching through 1,000,000 numbers. It took me 19 lookups. Okay, searching through 1,000,000 to find 99999. Now, linear search, what do you think? Okay, it took me 999,998, because I started at 1, not 0, to find that number because I went to war. I had to look things up. I had 1,000,000 lookups in this one. Now, it's super fast because of how fast computing is. But if we did this in the billions, or if we did this with other things, you'd notice the slowishness. Binary search, 20. It's amazing. Binary search was able to do it in just 20 lookups. This one took 1,000,000. So the efficiency that you get, and we're going to look at it in a minute as far as talking about efficiency is concerned, but the efficiency that you get when you use sorted data and can do a binary search versus a linear search is absolutely incredible. 20 lookups versus 1,000,000 lookups. That's really kooky. This code is going to be up on the web for you, so no worries about it. I don't mind you using it. I want you to understand it, though, so make sure you go in and read it and look at it and know what's going on. So when I come back here, I'll say present. All right, good. It brings me back to that page. So we did all this. We ran through all of this stuff, and I showed you 20 versus 1,000,000. That's pretty good. Read the slides. Slides are a good place to come here and look at the code and see about that. I think I added stuff to the step counter, so you get a lot more than just that now. But that's basically it. Binary search is incredibly efficient, incredibly cool. It's just like playing a game of high-low with your data in order to find things as far as searching is concerned. And that is one of the reasons why sorting or knowing about sorting is really, really important. The last thing we're going to look at, and we're going to look at it really quick. Again, I know I say this a lot. You're not going to be tested on it. You're not going to get, some kooky quiz question. You might get one quiz question. I forget about the efficiency of maybe linear or binary search or something like that. But big O, algorithm analysis is the kind of stuff that I just want you to be aware of. I want you to have seen it. So if people talk to you about it, you could say, yes, I've seen that before. Or, yes, I know what you're talking about. I know, a little bit about what you're talking about when you talk about that. And basically what it is, well, first time I heard Big O was about Oscar Robertson. He was a basketball player when I was a little kid. And there's also character in anime. But what Big O is really about is the analysis of algorithms. And the big O, the O is for order of magnitude. When we talk about how things work on a graph, we are talking about the biggest. If we look at things in terms of polynomials, we're talking about the biggest term. So if it's something to the fourth, plus x to the 3, blah, 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 we care about the fourth. We'll say big O4 for that because we're talking about order of magnitude stuff. And you'll see when we see the different lists, when we're talking about algorithmic efficiency, we're talking about things like constant. Like if I print my name, no matter what the input is, I'm always going to print my name. Well, then that's constant. Okay, no matter what, I'm always going to do the same thing. So I know that algorithm is efficient on a constant basis. It's always going to be the same. Then there are some things like linear search where it's tied to the size of your data. It's always n. You know how we use n for population sizes or stuff like that? N is always the size of your data. So like our linear search was 1 million lookups. So a linear search big O notation would be big O n. It would be tied to the size of the data. Okay? As you can see, and I think I grabbed this graph off of Wikipedia, there's different big O complexity numbers depending on what the algorithm is and what it does. If you look down here, you can see the red, the super efficient, almost 1-for-1 one is O log n. That's the efficiency of binary search. Okay, super efficient, super awesome. O of n, linear search, is right here. It actually looks efficient, but that's because this 100 right here and this 100 right here, you can see how they have the different skew as far as how big the graph is. Anyway, you can see that there are other complexities that get just absolutely bananas. This is the nightmare right here, n factorial. Those are computer science problems like traveling salesman problem and some other things that are considered what we call intractable. Very quickly, they get monstrous. Double the size of what you have on the checkerboard until you get to the 64th square and tell me how many things you have. You'll see that these problems get so big so fast that very, very quickly you get more possibilities for solutions than there are stars in the universe. And that sounds nuts, but it's actually true. Factorial will get you crazy. And that's basically what complexity analysis in computer science is. It's studying how much time we have, how much space we have, and how much computing we can do in that context, because there's a lot of problems out there. Well, not a lot, but there are some problems out there that are basically unsolvable. Some are unsolvable because by their nature they can't be solved. Some are unsolvable because they're what we call intractable, like the traveling salesman problem. Quite simply, if I have 6 cities, I need to find the shortest path to take to visit all 6 cities. Traveling salesman problem. What do you have to do? You basically have to take the combinations of all of those 6 cities and all of the different possible orders you can do them in. What you will realize is that once you get to 14 or 15 different cities, that number becomes massive. And you have to check every one because the answer could be in any one of those solutions. So that's when computer scientists realize, okay, some algorithms are intractable and we may never be able to use them, but maybe we can use hints and tips and things, little tricks to do things quickly. And those are called heuristics, and that's where we learn about heuristics and we learn about trying to do things that way. Big O is good to know if you're a computer scientist, because if you're going to create algorithms and you're going to take people's data and you're going to analyze it, you need to know how efficient things should be in order to detect problems, in order to know you're going to provide someone with a program that will run in a decent amount of time, that will, come to the proper conclusions, that will do a lot of things. So in any computer science curriculum, understanding the concepts of analysis of algorithms and being able to, deal with the different speeds and the different efficiencies going on is all part of the program. So I just want you to be aware of this kind of stuff. I'm not going to ask you 3 different algorithms, what's their complexity, and compare them to something else. Boom, boom, boom. I'm not going to do anything like that. I just want you to be aware of it and to see it. I think there's something else from Wikipedia that you can review or look over. So that's big O notation. You'll see the constant here, log n, and you can see all of the different algorithms that are the different efficiencies and things like that. So, okay. So that's it for this particular review video. I just wanted to go over the basics of sorting, searching, and big O with you. You'll see in a couple days I'm going to release the assignments. The second assignment has to do with reading a bunch of random numbers in and then running searches on them. And like I said, you can take the code. I'm going to put it up on Sakai for you. From this particular video, go nuts. Okay? Go crazy. Use that code and to do your binary and your linear searching. I don't mind that at all. All right? This unit is, like I always said it, you spend the first 3 units learning Python, then you're going to spend the next 3 units, this unit, the next 2, using Python. So this is the one where I'll give you the code and I just want you to study it and learn it, and I want to, give you a break. We got to start making this fun again. And then you're going to get to unit 5, and then you're going to learn about object orientation, and then it's going to be real fun. Everything's going to break open. All right? So that's pretty much it for this video. I am not going to kill you with announcements, because I am going to kill you with announcements when I'm done shooting the Class 3 video, which you should get tomorrow. I'm shooting this Friday night. I may do the Class 3 video later tonight. I may do it tomorrow. I don't know. I haven't decided yet. I will hit you with all the announcements then. Suffice it to say, I think tonight is the 4th. I gave you an extra day to go ahead and do your midterm project. Over this weekend, I will be releasing the information for the final project, so you can get going on that. And then Hans and I will we'll get started on Unit 3 grades. Grade-wise, I think everyone's doing okay so far. Everyone's AB. Everyone is fine. Things are moving along. You have my apologies for my not having more time to spend on this. I've still kept class going along, but I would definitely be more annoying and more in the forums and more doing stuff if I haven't gone through all the nonsense that I've had to go through with my leg this semester. But hopefully that gets all squared away and everything gets fixed up soon, and we can forget about that nonsense. Other than that, thank you very, very much. All the people have sent me emails, all the warm wishes, all the nice things everybody's been saying. It's definitely been appreciated, and I can't thank you enough. And don't worry about it. Everything's going to be fine. Come hell or high, even if the leg falls off, we're going to get you some Python, and you're going to move forward and have incredibly successful data science careers. All right? Then I'm getting out of here. But I will be back later this weekend because I got to give you that Class 3 video. Maybe I even do the recursion video. I don't know. I hope to get a little Python crazy this weekend and get a lot of stuff done that I haven't been able to do in the past couple of days. All right? All right. Then you be good, and I'll talk to you later. All right? Bye.